So we can start off with any law, and the book starts off with a different law in chapter 11, but it's really good just to focus on what we're doing right now and the relationship right now. And that's what you're looking at. It's called Gay-Lussac's law, and I'll leave this up here. Okay. So again, Gay-Lussac's law says So Gay-Lussac's law says that pressure of a gas is directly proportional to the Kelvin temperature. We had to use Kelvin to come up with our constants. When the volume and the number of particles of a gas is kept constant. So we need to keep two things constant during the experiment. We need to keep the volume. So the flask, I think the flask, do you think it changes in size as it goes from hot to cold? Do you think glass expands and contracts as it goes from hot to cold? I think solids are going to expand and contract a little bit. I don't know how much that will affect the results, but if you want to do a real good job, you'd make sure you have something that doesn't expand and contract a whole lot. Okay, a rigid container. Okay, and hopefully you didn't spring a leak. Because if you spring a leak, then what happens, there's molecules that can go in and out. And you guys know if you increase the number of molecules, the pressure will go up. And if you let molecules out, the pressure goes down. So we want to make sure that everything stayed constant. Okay? So I'm going to go ahead, I'm going to get off this screen here in a second. And we're going to go ahead and do a little bit of a problem here before you guys go today. You won't have any homework. Okay, I'm going to switch screens. Even if you're not done, I can come back to this later. So, you guys took pressure divided by temperature, and you came up with a constant. Okay, right? And you guys were coming up with like 0.3 something. Okay? Pretty consistent. So, what we can do is we got a sample of a gas. Let's say trial 1 and trial 2. Let's say you have trial 1 and trial 2 and you have the results for it. Basically, this is trial 1. This is trial 1's temperature. And then you're going to compare it to trial 2's temperature. They're going to equal, right? Because they all come out to the same constant value. So this is the law. This is Gay-Lussac's law. Mathematical portion of it, right there. P1 over T1 equals P2 over T2. So what we can do is we can, like you did on the 400 and 200, you don't have to have your graph to do this. All you have to do is have a beginning pressure. P1 and T1 would be beginning pressures. they're beginning. And then P2 and T2 are going to be a second pressure and temperature. And we'll just say that they're final. That's going to be final. So you got beginning and final. Or initial and final. A lot of times it's initial and final. Like in physics, they always talk about initial velocity, final velocity. Okay, so I'm going to introduce to you just one problem. Okay, and then we'll talk about it tomorrow a little bit too. So here's the problem. Okay, so here's the scenario. So we have this container and it's sealed. And we measure the initial temperature and pressure. And the initial temperature is minus 35, kind of like in lab. And then the initial pressure was 0.795 atmospheres. I'm introducing a new pressure to you guys. It's not that big a deal. It's another way to measure pressure. If you go in your notes, there's different ways to measure pressure. So then the final pressure is 2.13 atmospheres. Okay, you guys have that? So let's label the different parts. So we've got P1, B1, I'm not sorry, not B1, T1, P2, and T2. Let's go through and label. So what would this be here, minus 35? T1. Okay, now, here's the problem. It's in Celsius. And so, if you get a chance, you don't want to write in the book, but if you get a chance, you automatically have to change that to Kelvin. You don't. You never want to leave it in Celsius. I don't know how many tests that I do. The students will leave it in Celsius and get every single problem wrong. You gotta, in your head, right away go, I do not like that. I don't like Celsius. I love Kelvin. Kelvin's where I need to go. So then I automatically say 273 plus a negative 35, and that would be my new Kelvin temperature I need to use. So what would be the Kelvin temperature?
238.
238. And then I'll write that over here. 238 Kelvin. Okay, what's this? Pressure 1. 0.795. Okay, what's this? P2. Second final pressure. So that is 2.13. So here's the deal. We need to solve for the new temperature, and it'll be in Kelvin. Okay? So I'm just going ahead and erase this top portion since everything's on this page and I didn't leave myself enough room to do it. So I'm going to erase this top portion. And I'm going to do my setup. So P1 over T1 equals P2 over T2. Now this is the way I like doing it, and you guys don't have to do it this way. But what I'm going to do is I'm going to make everything on one level plane, and I'm not going to have anything in the denominator. So right away I'm going to cross multiply. So then it's P1 times T2 equals P2 times T1. I'm going to simplify it. That simplifies it for me. Most of you need to simplify it because you have a difficult time solving for a number in the denominator in the equation. So now I've done part of the work. So then if I want to solve for T2, what do I need to do to this equation? So I want to solve for this guy right here. What do I need to do to solve for it? Isolate it. So I'm going to do what with the P1? Divide both sides by P1, right? So P2 times T1 over P1. Now, if the temperature's going, or the pressure's going up, what should happen to the temperature? What should T2 be? Higher or lower?
Higher.
If the pressure goes up, temperature's directly related. So it needs to go up. Okay? So if you plug those in, you should get a number that would be a higher temperature. Okay? So it looks like it's going up. The pressure's going up about 3 times, 2.5 times. So my temperature should be about 2.5 times bigger. Does that make sense? So logically, if you can look at it that way, that's what you can get. So then that would be your final answer. So all I do is cross multiply. So then I set my variables up to maybe make it easier to solve for it. Okay. So it's going to be 2.13 times 238 divided by P1, which is 0.795. My answer is 637 Kelvin. So T2 is 637. Okay, and if you want to, you can plug it back in and see if you get the constants come out, but you shouldn't. There's no need to do that. Okay, all right. Whenever you get done with your lab, you can turn that in, make sure everything is answered. Okay?
Can you go back to that one with the law?
Yep. At this point, it's a lot of math we're going to be doing with algebra. That's it. It's really easy. Shouldn't have any issues with it. Solving for unknown variables. Dividing, multiplying to isolate your variable.
I just override.
That's all we're doing.
With that. And then
What is this lab?
Tomorrow. Should have it all done, or pretty much all done.
I had a